My background is certainly on the sort of scientific side of things. Working originally in growth chambers really was my introduction to humidity, growing plants and doing experiments with the Forestry Commission here in the UK. And then I joined Rotronic, which is a Swiss-based humidity and temperature measuring company. And here in the UK, obviously we're acting as a sales arm, but we also do a lot of training, consultancy, and we have a UCAS accredited lab here, so an ISO 17025 lab, so we can calibrate instruments. So yeah, my background is really in the instrumentation side and the measurements, but obviously we get involved in a lot of big projects in terms of building control, labs, pharmaceutical process lines and things. So hopefully a lot of the information has trickled in, and especially in terms of the training courses we do, we get a lot of engineers coming in with different levels of experience, and that's a great way for me to learn, and obviously us to try and educate themselves. So diving in, if we can, just a brief overview of what we'll talk about. So yeah, introducing why is humidity important. Obviously the world is changing, things are changing with that, but humidity has always been measured for different reasons. But focusing on the built environment, we'll be looking a little bit at why humidity is important. The world of humidity is fantastically broad, and that's what makes my life interesting, but try to keep it focused on 4 key areas: human comfort, human health, I've called this conservation, but sort of maintaining equipment, maintaining artifacts and things, and then energy and efficiency, which is clearly one of the biggest drivers now for a lot of modern buildings and new buildings, and obviously refurbishments going on. So starting with human comfort. Essentially, humans, one of their best ways of regulating their temperature is through sweating. So I'm not talking about pouring the sweat, but just evaporation of the moisture on your skin passing through the dermal layers there takes away the temperature, so it's cooling you down. And of course, in a high humidity environment, that evaporation rate will be much slower, whereas in a much drier environment, much lower humidity environment, you'll evaporate much quicker, and so you feel colder. So you can actually regulate how people perceive temperature by controlling the humidity. And obviously there's questions as to what is easier or more efficient to control actually temperature or control humidity. Good example is when you get off a plane. Planes are famously very, very dry environments. They've been flying up very high. They don't want to carry any water, so the air conditioning ensures you've got a very, very dry air. You come out of the plane and that swathe of humidity hits you, and it feels very, very hot. For us in the UK, that's also because we've probably flown somewhere far warmer than it is here. But yeah, it's often the humidity that gives you that real heavy feeling. Just as a bit of background, the 4 key areas that affect human comfort are temperature, and that's a combination of the radiated and the actual air temperature. And radiated being important as we replace traditional lighting with LED lighting. Clearly we're reducing the radiated heat effect. And then of course humidity, as mentioned, but also air velocity is important. If we're blowing air fast over people, you will feel colder. So that's why a fan, despite the fact that it's blowing the same temperature air over you, makes you feel a little bit colder because of that evaporation effect. Unfortunately, it's not that easy. There's other aspects individually in terms of what clothing perhaps people are wearing, maybe their metabolic rate, have they just eaten dinner or lunch, and of course just genetic factors, personal feeling as to when you feel cold or hot. So but the idea is we're trying to hit the largest percentage of people to keep them from complaining or faffing around with the control systems in your building or opening windows. So there we are, human comfort. Human health, it's not really, humans are pretty capable of suffering all range of humidity conditions, but there are other things in the world that thrive or don't thrive in different humidity environments. So this is really what we're talking about. Example being dust mites, for example. Very, very low RH will kill off dust mites, whereas higher RHs, they thrive a lot more. And asthmatics in the world and allergies and things are often caused by these sorts of critters. Pathogen survival in air is an interesting one. For example, viruses, they actually die, even though they're technically dead, I guess, but they become non-viable in more humid environments because of the moisture getting involved in some of the the molecules and chemical processes. Whereas on the flip side, things like spores or bacteria that you've sneezed out of someone who's ill, they will float around in very dry air for a very long time. So they'll move through the air and get inhaled by someone else, much more in low humidity environments. Whereas in normal humidity, sort of 40 to 60% again, they will pick up a little bit of moisture, get a little heavy, and then drop out onto the carpet and be hoovered up as dust, essentially. So pathogen survival can be an interesting one, but really you're looking for sort of 40 to 60% is best. The idea of lethal viruses is unavoidable, but there we are. And again, that's why planes are a real big problem for spreading illness, because it's a very, very dry environment. Your mucous membranes dry out, and so you're much more susceptible to getting infected. Finally, and probably more relevant to the buildings itself, is the idea of mold. And this is really down to high humidity and poor ventilation. So in the UK, we've got a lot of old buildings with external walls, maybe having a slightly colder temperature. Put a nice large bit of furniture up against that, you get poor ventilation. So as the wall temperature cools, you maybe get a little bit of condensation forming, and that encourages mold, and away we go. We have the nasty sort of examples we have here. Obviously, that then causes health effects as well. So really, all you need to do is try and keep the RH reasonable and ensure you ventilate. Virtually always, certainly in the UK here, outside air will have a lower RH than the inside air because it's colder outside. So ventilating, if you've got students, children out there in student accommodation, which is a classic one for mold growth, then get them to open their windows just for 10 minutes, and that'll ventilate the room and ensure you're keeping things a little bit more respectable. So moving on, conservation, a little bit more into obviously the museum and heritage side of things, but a lot of old buildings can be affected by condensation, really. So again, mold and rot, even just unsightly condensation on windows. It's all around humidity being too high, and parameters that we'll come on to called dew point, where as the temperature of the surface of, say, a window drops below the dew point of the air, you see condensation forming. In particular, that's obviously important for museum artifacts. They will require typically a stable humidity. So different things will require different humidities. Some, maybe books need dry, oil paintings need something different, but consistency is usually king, because the waxing and waning of humidity causes stress and strain. But perhaps a more common, certainly nowadays more common, is record stores, maybe things like server rooms, where electronics need to be in reasonable condition. So you're not getting condensation due to high humidity, but you're also avoiding static discharge due to very low humidity. Static buildup, you have natural grounding in higher humidity air, because the water molecules essentially act as an ability to ground any charges building up. So very, very dry environments will lead to static buildup. So on a cold day, you'll find you may get a lot of shocks off door handles and things, and that's because the very cold air outside is coming in, giving a very low RH, and you're getting these shocks. And finally, built energy and efficiency. It boils down to, obviously we all want to be green, but equally energy bills constantly on the rise. A good building is an efficient building, and it's saving the owners money maintaining that. So it's pretty well accepted that better measurements and better control will reduce the costs. You're trying to reduce the curve up and down, the oscillations of rooms as they overheat, overcool, overhumidify, etc. But equally, we get involved an awful lot, and I'm sure you do as well, in building environments for sensitive products. And this is where we're creeping into the idea of a bit more into industry, process control. We could be talking in this picture, I think this is PCB or silicon wafers they're storing there, but pharmaceutical is obviously a huge industry with very, very tight requirements on temperature and humidity control. But also in processes, it's about saving time. Ensuring consistent products typically means less wastage, usually less costs. But probably the big driver for a lot of people nowadays, certainly in food and pharmaceutical, is regulation. And there we see that also creeping in with building control and requirements, governments pushing industry to have higher standards for what they're doing. So that gives us hopefully a bit of a background into some of the applications I think that are hopefully relevant to you, and why we're interested in measuring humidity, and perhaps ensuring that it's measured to a reasonable standard. So if you're still awake, we'll go into the a little bit onto what is humidity. So I am going to start quite basic here, and I apologize for that, but I want to give everyone a good grounding. Humidity is not always an easy thing to grasp and understand really what it means, and I think if you can get that, then it really will help you. If you understand it, then you can understand how to measure it, how to control it, etc., etc. But we'll talk about the states of matter. I find this a good way to introduce what humidity is. Then we will go a little into detail as to exactly what relative humidity is. But probably a lot of you will be using things like mixing ratio or enthalpy, and so we'll talk about what they are and perhaps why they're used briefly. So, states of matter. Water, clearly in its solid state, we all know as ice. And to be quite simple, it has a definite shape and volume, and the particles packed in that state, they're all packed closely together, and they're only rattling around, they're only vibrating around. It's good to get your head around the idea of what particles are doing, and I'll use it over and over again because I think it gives a sort of bit of a visual cue as to what's going on when we talk about some of the things we go into. So this is just near Lake Baikal in Russia, so very, very cold. I think it was about -40 that day. But very, very dry, so it didn't actually feel particularly cold. But anyway, very cold, and there I am throwing myself down one of these silly ice sculptures. So that's solids. Liquid is fairly similar, except it only has a definite volume. The shape, it will flow to fill a container or a space. The molecules have got a little bit more, little bit less packed so closely together. A bit more able to move and flow around each other, and obviously they've got more energy because they're warmer. So the ice has melted, and so they're flying around with a bit more energy and able to flow over each other and fill a volume or fill a container. And here we have a lovely sunset of the rice paddies in China, and it's always one trip. I went from Russia down to China. Water vapor or gas. So water in its gaseous phase, we generally describe or call it water vapor. It has neither volume or shape. The particles now are really fired up. They've got a lot more energy, and they're able to just fly around and fill or expand to fill a space. And so often a common mistake is people think clouds are water vapor. They're not. It is as soon as water vapor, you see it as a cloud, you've got actual droplets of water there. So that's back to the liquid phase. Here we have water vapor in that space. We can't see it because clearly it's a molecule. So it's only a single molecule of water. How on earth could we see that? It's only when they clump together and form a droplet of water that we can see it. So water vapor is what we're talking about when we're referring to humidity. And of course the boffins out there will know that there's plenty more states of matter, but we're going to stop there because it becomes totally irrelevant. So the only equation I think I've got in here is Dalton's law of partial pressures. I dare say those of you balancing systems and dealing with HEPA filters will know this better than me, but all I want to get across is that air, the gas mixture, but the example being air, that the pressure of it is a combination of all the partial pressures of each element in that air. So the bulk of air being nitrogen, there will be a partial pressure of nitrogen, say something around 800 millibar, then oxygen, and then water, and then less and less of other bits and pieces. So obviously ambient pressure is around about 1000 millibar, slightly above sea level. So the term we're getting at here is that the partial pressure of that gaseous water, we often call the vapor pressure. So that's what we're referring to here. We're drifting away from humidity, but it'll bring us all back. So pressure is a combination of all these aspects, and the vapor pressure is the water aspect. So now, just to summarize a typical sample of air, if we had air with absolutely no water in it, which would probably be quite hard to achieve, but if we did, we have 0% water. This is by volume, so we're not talking about humidity, just by volume. So 0% water, and as I said, sort of roughly 80% nitrogen, big chunk of oxygen, and a few other bits and pieces. Typically dry air is around 0.5%, probably closer at 23 degrees to 1% by volume of water. Normal climate around 1.5. Very wet air, this graph's actually slightly wrong. It would be wet air at about 30 degrees would be at about 4% water. When I say wet, I mean very humid. So again, not necessarily walking in a cloud, but we're very close there, very, very humid air. So not a lot of air, not a lot of water in air by volume. If we stick RH values on there, then we see pure air, unsurprisingly, with no water in, has 0% RH. Dry air is around about 12% relative humidity, and then 35, and then up at 95, near what we call saturation. So this RH, this percent RH unit, is fairly unassociated with volume. So what are we talking about here? Before we go any further, just a little recap, the important bits. Oh yes, that's one thing I didn't say. I'll just go back if I can. As we said, ambient pressure is around about 1,000 millibar. So as such, if this water vapor pressure we're talking about between 5 and 40 millibar of water. So the vapor pressure is around about between 5 and 40 in normal air, unless it was very, very hot. So just to recap, water in the gas phase we call vapor, or vapor, water vapor. Water vapor is transparent. If you can see it, then it's liquid. We've said the amount of gas can be stated as a partial pressure. So for water vapor, it's the vapor pressure of water, partial pressure there. The air, we've said, typically holds somewhere around about 1 to 4% of water vapor, which is 10 to 40 millibar as a partial pressure. The most important thing to say is that air can only hold a limited amount of water vapor. Now the reason for that, if we again go back to our jiggling particles, and you imagine we have a situation where we've got some water vapor in the air, we start to add more by whatever means, the molecules are starting to bash into each other, they're getting a bit crowded in there. They're still moving around at the same speed, but as we squash them together and they're knocking into each other more and more, they start to sort of stick to each other and hence form droplets of water. So as we pump more water vapor in, eventually we get to a point where you would see a sort of cloud forming, or on a cold surface you'd see condensation forming. Very hard to actually create a cloud, but apart from up in the atmosphere. But in your, I guess in your steam room you might do it, but it's probably not actually true 100% humidity in the simple generation sense we're talking about. But anyway, molecules getting closer together, forming water droplets, and that's why air can only hold so much. But most importantly is that hotter air can support more water vapor. And again, that perhaps makes sense if we think about these molecules. They're starting to bash together, but if we heat them up and they therefore speed up, they're less likely to stick together. So they're flying around much faster now, they can bash off each other, and we don't see them moving into the liquid phase. So hotter air can support more water vapor. And just some final terms, just so we can all speak in the same language. When air can hold no more water, at whatever temperature is, we get to the point where it can hold no more water vapor, we call it saturated. Makes sense. And the vapor pressure at that exact point is called saturation vapor pressure. So that's probably the most important bits of this bit. And this helps to give us the, hopefully you've all seen a psychometric chart, and this is where, if I just highlight that line, this is where the this line here comes from. This is 100% humidity. It is the saturation vapor pressure, and the important thing we can see is that as the dry bulb temperature, so the actual ambient temperature, increases along this bottom scale here, we see the saturation vapor pressure increases massively. So what we're saying is hotter air can support more water, and that's where that curve comes from. So this is the key thing I want you to appreciate, is that temperature massively affects humidity. If you take home only one thing, that's probably the thing to take home today. Any humidity measurement is totally dependent on temperature. And if you're getting small temperature errors, you'll be getting big humidity errors. Just to come back to what is relative humidity, it is the ratio of actual water vapor pressure, so how much water vapor do we have there as a pressure, against what could be there, what the saturation vapor pressure is at that temperature. So it's how much water vapor is in the air compared to how much there could be in the air. And as I've said, it's extremely temperature dependent. We can go back to the chart here and see if we had a situation where the vapor pressure, let's say, was somewhere around, I don't know what the exact value is, but we've got it in specific humidity here of 10 grams per kilogram. So if that was the actual amount of water vapor we had in terms of vapor pressure, we can see the maximum is up here, so we're about 50%. we're slap bang in the middle. Maximum's 20, we're at 10, so we're talking about 50% RH. If we heat that air up by, say, only 5 degrees, maybe 10 degrees to keep the math simple, we can see we go to more like 30% RH. Nothing's changed. The amount of water vapor in there is exactly the same, except we've changed the RH. So that can be a real headache when controlling RH. If you're taking cold air that you see has a nice high RH, maybe 80%, 60% here at 10 degrees, and we move it up to 23 to keep everyone happy, we can see straight away the humidity goes low. So if you were controlling on humidity alone without any intelligence, you'd have the dryers going absolutely crazy, heating the air up, and then coming in and it'd be totally way too dry. You should put it down low. So you need to understand as air moves and temperatures change, humidity is often doing strange things, but very predictable things. That's the key thing. So just to visualize that a little bit more, what we've got here is just an example trying to show the effect of temperature on humidity. So the idea of this is these blue blobs are the actual water vapor pressure, and the slightly pink blob is the saturation vapor pressure for the gas at that temperature. So we can see at 10 degrees we're nearly saturated at 99%, but if we heat that air up just by 10 degrees, we can see the saturation vapor pressure massively increases, so therefore our relative humidity drops to 52%. Another 10 degrees, slightly less pronounced, but it goes down to 28. The key point we're seeing here is that just 10 degrees change. So for every single degree, we're getting roughly a 5% change in RH, and that's a good rule of thumb at roughly room temperature. A single 1 degree error in your temperature measurement will lead to a 5% error in your humidity measurement. So you can see it's quite difficult with maybe even a 0.1, 0.2 accuracy temperature sensor to still get very good accuracy humidity measurements. Now below this, we're introducing another parameter. There are a number of parameters that are unaffected by temperature, and that makes them very handy to use, especially in building control. So this is dew point. So we can see here that at 10 degrees we're not quite saturated, but if we dropped that temperature just slightly to 9.85, we would hit 100%, and we'd see condensation, or we'd see liquid water somewhere. So that's quite a handy, it's quite a practical value to use, dew point. It's also measured with very high precision instruments. The real top spec instruments are dew point instruments, chilled mirror instruments that cool a surface until you see condensation forming on that surface. So a classic example is you take a Coke can out of the fridge, or any other drink, of course, and it'll be probably quite cold, hopefully 5 degrees. Chances are you'll see condensation on the can surface because the surface is colder than the dew point of the air. So we can see here, as the RH changes, the dew point is exactly the same, and that's the same for other parameters like enthalpy or mixing ratio. Then I think, yes, we come on to next. So just to mention these other parameters, there are many other parameters that are used. Excuse me. Traditionally, for traditional reasons as to how they were measured, or different instruments, or different engineers doing different things, the key point is that most modern instruments can now measure humidity and temperature, and they will give out these outputs if you need them. So if you have a control system that requires an enthalpy input, your instrument supplier will almost certainly be able to supply an instrument that is configured to provide that analog output, or that digital output. So you can hot swap, essentially, easily swap in a new instrument without having to rely on some ancient old instrument that is designed to measure wet bulb, perhaps. So I've chosen these four. I think these are the most common in my experience. Probably not in building control dew point, but it's certainly a common one in calibration. And as we said, it is the temperature to which you need to cool the air in order for saturation or condensation to occur, so to get to that saturation point. And the real benefit of it is we can very easily see that occurring on a surface, let's say on a mirror, and if we measure the temperature of the mirror, then we can very accurately measure it by just using a temperature sensor. Mixing ratio, I would say, is probably the most common for building control in my experience, but obviously depends on different areas, I guess. And this is the mass of vapor per unit mass of dry gas. So it's just a parameter. It doesn't really have a dimension, but virtually everyone I know uses grams per kilogram. So typical scaling on perhaps an analog instrument would be 0 to 25 grams per kilogram mixing ratio. So that's quite commonly used, and again that's temperature independent, so you can control the mixing ratio of an air and deliver it at the right temperature, and you will get the RH you need. We'll come on to that. Wet bulb, another practical measurement. This is the temperature. So evaporation, it comes back to evaporation. It's the temperature of a thermometer covered with a wet wick that is having the ambient air passed over it, and as that water evaporates, it will depress the thermometer's temperature, and that difference in temperature between the dry bulb temperature, so the temperature sensor without any wick on it, wet wick, will give you a measure of the moisture content, which can then be used to calculate relative humidity. All these parameters can be calculated back and forth between each other. All you need is temperature, the specific humidity, some measure of the humidity, or the relative humidity, and the pressure. And normally we assume ambient pressure, but obviously if you're working in a pressure application, that may change things. Finally, enthalpy is quite handy for air conditioning, because it's a measure of essentially how much energy you're going to need to put in to heat the water up. So enthalpy is the energy of the dry air and the evaporated water in that air. So, excuse me. Obviously, as we add more water vapor, you need more energy to heat up that water vapor as well, and so your heating system will need more energy to heat humid air than it will dry air. I don't know whether very advanced building systems take that into consideration or not, but it's something, it would be an interesting one to explore, whether drying air and then heating it and then rehumidifying it is preferable to just taking humid air and heating it up. Something for you guys to tell me, I guess. Okay, so let's move on to the practical bit, a bit more interesting. Overview of the instruments, a little bit of history, typical measurement problems that we see, and some guidance on best practice. Again, skimming through this quite quickly, but hopefully give you a bit of a feel of what we're talking about. So certainly not used in building control anymore, but the two sort of older instruments that used to be used to measure humidity were mechanical systems, basically relying on the properties of some sort of product, horsehair or catgut even, to stretch and strain due to the humidity and give a difference measure, and usually mechanical, literally by moving a needle back and forth. Pretty poor accuracy, fairly poor repeatability, clearly, and very slow to respond. They're not the best instruments, but they're great for simple indication, and you'll find a lot of people with their home sort of weather systems will perhaps have one of those on the mantelpiece. But yes, not really used anymore at all. Psychrometers, which is the term for this wet and dry bulb type system, they are still used in a lot of dirty applications, so industrial chambers, perhaps even brick manufacturing, because they're fairly rigorous. They're just two temperature sensors, quite hard to destroy. But the problem is the reliance on having a very clean wet wick, has to be maintained wet, has to have very consistent airflow over it, is quite difficult to ensure. So easy in a small chamber environment, perhaps, where you've got sort of specialist engineers keeping track on things and regular calibration, but in a building situation it would be really quite difficult to use. Although you do still see occasionally people using them as perhaps a reference instrument. But one of the chief scientists at the National Physical Laboratory here in the UK, so our National Standards Laboratory, describes a whirling hygrometer, so the classic spin it around above your head hygrometer, as being as accurate as a banana for measuring humidity. So essentially being very poor. But if they're used well, and if you know the skills to do them consistently, then you can get a good measurement with them. But not really used in instrumentation. So what is used? Pretty much 99% of the time will be what are called relative humidity sensors. They're very widely used, very practical, lots of different instruments out there on the market from different price points depending on your accuracy and what you need from them. But basically they rely on the electrical properties now of products. So instead of the mechanical properties of things like hair, we're using the electrical properties of typically strange polymers, special polymers that maybe change in their resistance or their capacitance. They're the most common types of humidity sensors. So people have developed these polymers. They find that they seem to respond fairly linearly to this measure of humidity. They don't normally respond to absolute humidity, so things like mixing ratio, they're not linear to those. They do actually respond to relative humidity, and they are then factory adjusted in some way to give accurate RH measurements. And this is an example of a typical sensor. So they'll normally have some kind of protection filter just over the sensor itself. Sometimes they're bare, but some kind of layer over them. And then the idea is the water vapor passes either through the sensor itself or just off the surface. Some of them are bonded onto the surface of something, and they just interact with the surface there. Obviously, an electrode and a dielectric, creating in this case the capacitance, and they're connected to some form of electronics. So there'll be electronics with temperature compensation on good instruments. Normally goes hand in hand with temperature measurement to get the best precision. But they're quite delicate. That's the problem. Well, let's move on. So pretty fast to respond. We can get really fast sensors with about 1 micron thick. So they're used in weather balloons that respond very quickly. Pretty robust. Fairly wide operating range, typically minus 50 to 100, maybe 200 degrees, depending on the application. Humidity is fairly pointless below 0, but you can measure it. And fairly low cost. You could probably get, your fridge magnet humidity sensor is probably something in terms of pence that's put on there, or pennies, sorry, cents, whatever you want to call it. But decent humidity sensors will be maybe sort of 10 to 30 pounds at the sort of production cost or end user cost as an OEM. Then they're built onto electronics and housings and things, and you can pay for an ATEX instrument maybe up to sort of £1,000, £2,000, but typically somewhere between maybe £50 to £200 for a typical humidity sensor. Not fantastically stable. They, unfortunately, because they're small polymers, any dirt and interactions and things with them will cause them to change their behavior. They are dependent on temperature. They will measure humidity accurately at one temperature, and as you move away from that, you will start to see errors. Because of this instability, they drift over time, and that's probably one of the biggest killers. And things that are normally ignored in building control. A very good sensor will drift less than 1% a year in a clean environment. Maybe you get better, but typically that's about the best you can achieve. A lot of sensors will drift 2, 3, 4% a year, and if you're trying to control very precisely that drift, forget your accuracy that you started with. That drift is the big effect. And then contamination, of course. If there is dirty environment, contamination is a big problem. How am I doing on time? I think I need to speed up a bit. Yep. So the biggest issue, as we said, with taking measurements is temperature effects. You need to ensure that you're getting a very representative measure of the temperature. So get that sensor in deep in the duct. If you're taking spot measurements, ensure you've got good stabilization. Be wary of stem conduction. So a transmitter here at 25 degrees, let's say, outside a duct, could be even colder in a plenum perhaps, but going into the duct, for whatever reason, at 55 degrees, there will be stem conduction through that. You've got electrical wires in there. They will conduct temperature just as well as they conduct electricity, so you'll get an error. Also, cheaper electronics self-heat, so high voltage transmitters will generate a lot of self-heating. I'll skip on. Pressure effects ultimately don't really affect humidity, relative humidity measurements, but they will affect other parameters. So just be wary. If you're using other parameters, pressure can affect. And as I said, drift is one of the probably the biggest issues, and the only way you can deal with it is either replace your sensors, which most people don't want to do, or you do regular calibration. And it may be you only need to calibrate or spot check sensors in certain locations, but yeah. Contamination, and this is really speaking with your suppliers, ensuring you've got the right filters. I think I mentioned filters again, but ensure you've got the right filter for the sensor. If it is in a dirty environment, ensure you're replacing that filter. As the filter clogs up with muck, you're going to start measuring the muck as opposed to the air. So you can see here particulates forming, corrosion from hydrogen peroxide for when areas get sterilized. So perhaps regular replacement of filters, or be wary of nasty chemicals can really wreck sensors. Painting sensors is not good, it happens. if possible, take them out while the rooms are being painted. The solvents will really damage the sensors. So yes, if you're doing spot checks, if you're doing commissioning, ensure that you've got some sort of traceability if you can on your handhelds. I appreciate we don't all have endless budgets, but if you haven't got any traceability on your handheld, and if it's sat in a drawer getting dusty for 3 or 4 years, then how do you know what the measurements you're taking are? If you're working in ducts, ensure good insertion and good seal for when you measure those ducts, and let things settle down. I think I mentioned stabilization time. Sorry, I'm skipping through this, but I'm conscious of time. Yeah, so we have a building project where it's lab-based, so it's a little bit precision, but we tell the people there to ensure they leave the commissioning logger in the room for 30 minutes, close the doors, let everything settle down, and ensure we've got really, really good stability. You can see a classic curve here. At this point, here, you can see that the apparent stability, it appears to be a flat line, but give it a little bit more time and you'll see does it settle down even more. And you can start to see also the oscillations if they're there. And also be sure you're measuring and you're aware of the temperature effects. Don't put something next to a heater or a bit of electronics, a PC that's chucking out lots of heat. Regular calibration if possible, and also don't forget the analog errors. So a lot of analog systems, can you loop check? So can you check back the entire analog loop back to the BMS system to make sure you're getting rid of any analog errors there as well. A lot of buildings have sensors put in, BMS systems get updated, and you find you're replacing a sensor and it's apparently connected in another room. So things like that are often a real gripe for quality control. So a little bit of a touch on some common sense really on sensor locations. As said, avoid close proximity to heaters in heating systems. Get them back past that if you can. Cooling coils, steam injectors. Humid water is really bad at going into the vapor phase, so you don't want droplets of water hitting your sensors. That really wrecks them and gives them bad measurements. So get them well in advance of the past the steam injectors if you're using those, and obviously high air turbulence and things can mess up sensors. Here, just saying, get a decent insertion, in this image here, decent insertion, decent glands to ensure a tight fit. If you can't get decent insertion into the duct, consider doing it on an L bend and placing it into the airflow of the duct, and that will reduce any stem conduction. So all fairly obvious really. In rooms, ideally, putting things on a wall is pretty standard, but clearly the wall will have its own thermal effects. So if it is a lab environment or a very close control environment, maybe have the sensor hanging from the ceiling. So moving on, this is just very briefly to touch on the idea of using, say, a parameter like grams per kilogram. Let's say our desired condition is 50% RH at 23 degrees. That gives us a mixing ratio of 8.74. All we need to do then is ensure that our control system is delivering 8.74 grams throughout the system. So it may be back in a duct that's at 18 degrees and it's going through another precision, slightly more precise heater system, but that's right. Get it to 8.74. As soon as that air comes into the room and warms up to 23 degrees, we know it will be exactly 50% RH. Quite a simple and elegant way of doing it, and that's how a lot of building systems are set up. And it's this idea of getting this absolute humidity window in the air handling unit and delivering that to the room, and as long as the room's at the right temperature, then we're going to be spot on with the humidity. Just a note on outside air sensors. If you're using them, make sure they're on a north-facing wall, in a weather shield, and away from heat sources and things, so you get the best measurements. How are we doing? Yeah. Finally, a note on accuracy. Measuring humidity is not easy. The national standard here in the UK claims 0.1 to 1% uncertainty for humidity. Doesn't matter if you don't know what uncertainty is, essentially error they can calibrate to. For temperature, they can stick in 3 zeros before they add a number to give us the accuracy. So they're 3,000 times better at measuring temperature in our national standards lab. So humidity is not easy. The best RH sensors claim maybe 0.5 to 1%, the very best. So if you're trying to control to say 5% plus or minus, and you know that 1 degree error causes plus or minus 5%, you can see it's not easy. So very close control for humidity is basically not easy. And the classic thing when someone puts a handheld next to a sensor and sees a 2% difference, is that actually a difference, or is it just errors on the two probes, or uncertainty of the calibration on those probes? It's a difficult one. So just be aware that it's not as precise as temperature. Don't expect miracles. So my sort of closing 3 points, hopefully hammered it home. Measuring humidity, it's all about getting a decent temperature measurement. So good humidity sensors will have a good temperature measurement, but don't forget sticking it next to your hand or having self-heating of electronics will cause problems there. Calibration fundamentally is the only way to really confirm what's going on in your performance. Obviously it's a cost, but if you are using a reference handheld, get it calibrated every now and then. Typically once a year is what people will do, and you can be confident that as you're commissioning, you're getting the right measurements. There's a couple of links here that hopefully will work on the PDF when it's downloaded. We did a CIBSE article on the National Physical Laboratory project that we worked quite closely with the installers there to get 0.1 degree control in rooms, and certainly better than 2% RH, not easy. We've also written a white paper on modern monitoring and control, just trying to give our thoughts on where the industry is going. So just to wrap up, obviously there are my details and the links to Rotronic. We're very happy to have a discussion if you've got queries. We have subsidiaries in most countries, or if not distributors, and we do all range of kit, including pressure and CO2. But hopefully that's given you an overview, and I'll very happily take any questions.
Great, thanks very much.
Which I think Tim is going to manage for us.
Yeah, there's a whistle-stop tour of air through humidity. So thanks very much for that, Jeremy.
No problem. Hopefully not too fast.
You probably covered what I cover in a whole lecture course there in 45 minutes. So well done. I've got some questions come in, and perhaps if I can start with a question on the actual sensors themselves. This one's coming from Alan, and he asked, the drift you were talking about in the sensors, is that in just one direction only?
That's a good question. Yes, thanks, Alan. No, sensors behave in very strange ways. So no, they will drift. Often you'll find that a particular manufacturer's sensor will drift in a particular way at perhaps a particular point. So we know Rotronic sensors tend to read a little bit high at the high humidities above 95%, and sort of drift that way over time. Manufacturers do clever things. They try to perhaps adjust it slightly lower to compensate for that. Not always a good idea, but no, they will often drift different ways, and often they'll drift one way one year and the other way the next year. They drift when they're not used, sat on the shelf, but commonly the main thing is, I guess they age on the shelf, but the main thing is contamination that causes the drift. But it's a very difficult thing, and finding the right sensor for your application. Sometimes, you know, a Rotronic sensor may not work in some application because of some weird chemical that just doesn't work with our sensor, and maybe use a Visala or whatever you want to use. Yeah, but most building applications, sensors are all pretty reasonable because it's hopefully fairly clean. That's the idea anyway.
Okay, thank you.
That helps.
Yeah, that's great. I've got a question here from Dan. He asks, he says, you mentioned the dew point control and the chilled mirror. Is that the only way that dew point can be measured?
Fundamentally, yes. So the fundamental measurement of what dew point is, which is essentially the temperature that water in vapor phase condenses, is a dew point mirror. But there are what are called dew point sensors, and they are basically capacitive, or they have things like sort of phosphorus pentoxide, funny materials that respond more accurately to the dew point, so they're more linear to dew point, and they are designed. They don't really work in the RH range as accurately. They're more for very, very dry environments. So when you go below 0 degrees dew point, RH is fairly pointless. Below 2% RH, it's not worth using RH. Dew point instruments are for those very dry environments, so process lines, maybe like diving gas, things like that. So they're very, very dry gases. You use a dew point sensor, and it's just a sensor that's designed to measure dew point. So they're the stat and the chilled mirror are all I'm aware of as typically used to use. But the chilled mirrors are maybe £5,000-10,000. So they're labs, essentially lab environments or power stations or calibration labs. Dew point instruments a little bit more affordable, and they're used in these drier processes, I guess.
I guess not to be confused with what we traditionally call dew point controls, where we sprayed the air till it was just about saturated, then measured its temperature, of course.
Yeah, okay.
And we just assumed then that the temperature was a dew point temperature, I guess, at that stage.
Yep. No, and if you have a system that you know is basically saturating the air, then yeah, you can make a very fair assumption that the gas, once it's passed through that, is basically saturated, or at least 99%. And so yes, it will have the dew point of that temperature. So yeah, that's I wasn't aware of that, but that's an interesting one. A lot of chambers are controlled in that way. Essentially, you have a big kettle making saturated air and heating it up.
Okay, well, thanks for that. Okay, we go from London now to Canada, I think, and this is a question from David. David asks, what do you recommend as a time period between calibrations?
It's a classic question. Really depends on the application. I would say we're often not allowed to say when things can be calibrated because it depends on your application. As an example, pharmaceutical industry in a very important environment, maybe a production area, they may check the sensors every 3 months and do a proper calibration every 6 months, maybe do an accredited calibration every year. Now that's fairly extreme and there's a lot of money behind that. Most, I would say, sort of building engineers using reference handhelds, ideally you should get it calibrated every year if you consider the amount of drift that you may have on the sensor. Now that may be something you can do yourself. You can use salts to do a field calibration, or you can compare against another instrument. If you're sending it away to a lab, again, depending on the accreditation you need, there's different costs, but typically a year. But I would say a lot of engineers don't do that, and certainly building sensors, clearly there's not probably the budget or the ability to take those sensors out and calibrate them if they have to be sent away. So I would say most building sensors are not calibrated at all. Exception being very critical applications, so research labs or such like.
And are you able to give us some idea of cost of a calibration?
Yeah, so as an example, we do a UCAS calibration, 3-point humidity at £190. We are a good lab, so we're probably a little bit more expensive. You could probably get a 3-point humidity calibration maybe to a traceable standard, so that just means they're using reference instruments that are what we call UCAS in the UK or NIST in America, calibrated, but you don't have that sticker on it yourself. And that probably you could maybe find a company that does it for maybe £100. So it varies, but if you combine temperature as well, add a few more points, obviously cost goes up. But yeah, maybe £100 to £200 is probably a reasonable value.
Okay, so $150 to $300 we're looking at for a calibration, US dollars. Yeah, okay.
Which can be a shock, obviously, when your instrument could be the same price, if not less. But there you are.
yeah, an interesting quandary. Just before I go on to some system questions, I just had a question here. Oh yeah, the question was on the good old true wet bulb thermometer.
Oh yes.
And the requirement is to use distilled water with those. Does it matter if people don't use distilled water?
It will just affect the sort of fundamental physics of it is it's the depression that you expect is based on pure water, on distilled water, very, very pure water, very clean wick. If you're not using that and there's other stuff in the water, it will evaporate at a different rate and therefore change the temperature depression, so you'll start to get errors. They may be minuscule in what you require, depends on your accuracy requirements. We get psychrometers back, the wick is disgusting, and and they're all dry and crispy. So yeah, the reality of it is in the field is that often they're not perfect, but it all depends on what are you trying to achieve. If you need an indicator at 10%, then fine, no problem. But if you want to do it perfectly, the MPL, they take account for which level of the building they're on because of the different ambient pressure. So, how far can you go?
Okay, thanks for that. Interesting question here. Of course, we're seeing more and more of adiabatic coolers. These coolers, spray coolers. A lot of people are using spray coolers, particularly with data centers. We're seeing them increasingly well used. And a question here is really the humidity control using adiabatic coolers. I guess it's almost going back to my traditional dew point controller, or temperature control. But is there any special concerns here with that sort of control that you know of?
Yeah, it's a good question. This is where my sort of building control knowledge falls away. But in principle, you would want to not measure the humidity where you're getting saturation. So where there is liquid water around you, there's no point measuring the humidity there. So if you did have an area of the system that had this cooling system in place, you would measure the humidity far enough away from that. Beyond, once the air's passed through, that's cooled down. Any moisture in it has then gone back to vapor, probably as the air warms back up again a little bit, and you would measure the humidity there. And you may be surprised, it may not be anywhere near 99% or 100%, but you'd certainly want to always avoid sensors condensing. And it's a good example of not putting perhaps a very cold sensor in a hot, wet duct, because it will act as a condenser straight away and will get saturated and take a long time to dry out. Sensors that get wet sort of stick at 100%. They can stick there for quite a long time. I guess if you in the proper control system, if you were measuring the air going in and the air going out for temperature and humidity, or for some absolute humidity value, that would be the logical thing to do to see the efficiency of your cooling system. But beyond just the temperature, but that's sort of as far as my knowledge goes on that.
Okay.
I'm afraid.
I'll move you on if I can, Jeremy. Of course, as ever, the questions are coming thick and fast as we head towards the end of our session here. An interesting question again, and another interesting question. This one's from Chris. I'm not quite sure where Chris is from, but Chris asks about the comparison of what could be reasonably expected. I'll read out verbatim. What could be reasonably expected from comparing two sensors? For example, in differential enthalpy control of an economizer or mixing box, because of course it's the actual difference in the measurement which controls that sort of a system. So it's important that the differential doesn't matter what the absolute is, as long as the differential is the same. What can you say about that?
Yeah.
What's the certainty there?
I must say I don't know at all what you're talking about in terms of the differential, but always admit when you don't know what you're talking about. But yes, a fair measurement with two reasonably accurate sensors. Yeah, it's a difficult one. If you were to put them literally side by side in a reasonably stable room, you'd kind of hope a 2% accuracy sensor to read within 2%. You'd want them to be reasonable. But there are so many uncertainties going on. So me breathing on these, one's going to maybe get more humid than the other. Hopefully you wouldn't breathe on them. So you're trying to isolate as many things as possible to avoid variation. And the fact that the sort of point I made about the accuracy in the national lab being essentially 1%, that is them doing everything they can to create a space that is very, very stable on temperature, and their sensor and ours, or whoever is being calibrated sensor, is absolutely next to each other, and they're getting 1% realistically. So you can put two sensors and get 3 or 4% difference. I guess what you have to start doing in these situations is hope that they're reasonably accurate, and if you're looking at a difference, that difference should remain the same over time. Okay, sensors will drift in different ways, but they hopefully don't drift too much. But it's how long is a piece of string? I mean, we state 0.8% on our sensors in terms of accuracy, and you would want them to be reading, within next to each other, left in maybe a little box so that they're vaguely stable for temperature and there's no air passing over them. You'd expect them to be sort of 1.5%, 1%, if not better. But we get people ringing up with sensors that it reads 2% out, it's broken. Well, put them back in the lab, put them next to each other, and they're absolutely identical. So it's a difficult one. There's no right answer, but I'm afraid. And if you're buying a £50 sensor with probably 3% accuracy and 2 or 3% drift over a year, could be wildly different.
Okay, I mean, interesting area. It's one I read about some years ago as where they put a number of these in a test cell, US Army, and found them drifted. The difference was enormous. But there's an ASHRAE research project that Chris has just told me about, and he's going to let's have that. So we'll pass that on to you, Jeremy, and then you were
fantastic. Fantastic.
Okay, we just probably got time for just one or maybe two questions if we're really swift. Let's just pick. Let's just show the breadth of our audience. I've had a particular question here about control of bridge deck humidity to prevent corrosion. I mean, it doesn't matter. It can be any metal. It doesn't matter to be on a bridge deck.
Yep.
I mean, are you able to give us any feel for how these sort of sensors are used in that sort of environment?
Yeah, definitely. It's actually quite a big area, especially painting, things like that. So humidity sensors are essentially placed inside a little weather shield, so something to protect them from the wind and the rain. And in marine environments, you might even have another layer to protect it from salt spray. But yes, you're measuring humidity there. And now, clearly, on a ship deck, you probably can't do anything about it, but at least you know. But perhaps the most relevant experience I have is with the painting applications, where you should not paint surfaces if there's condensation on them. And so the easiest thing to do is measure the humidity, calculate the dew point, measure the surface temperature of the thing you're painting, submarine or a ship, and if it's not if there's not a good difference between the two, then you wouldn't apply any paint because there's condensation on it. So it's certainly used for that sort of application and for equipment reliability. Obviously not easy, I guess, to control that, but I would say in any application, normally condensation is bad, unless it's you adding water through some method of condensation. But if you can avoid cold spots in your ducts because they nip outside with hot, wet air, and it's going to cause condensation, that's clearly not good. So avoiding saturation is usually the key, if you can. I don't know if that answers the question, but
it's an answer anyway, Jeremy. So thanks for thanks for that. And we're just about running out of time, but just a note. Relative humidity, it's actually a ratio of vapor pressure, and percentage saturation is a ratio of the specific humidity. So, Jeremy, it's been fantastic. You've covered such an enormous area, and I think we've all learnt a lot. So, thank you. I've got thanks flooding in here from our audience. It's been very good.